Now there's a special case for the parallel plate capacitor that's worth taking a look at, partly because it summarizes a bunch of ideas from earlier in the course, and partly because the derivation isn't very difficult. So we imagine that we're looking along the edges of the plate. So if you imagine that a sheet of paper in front of you is the plate, then you would first look at the sheet of paper as if you're going to write on it, and then just turn it 90 degrees so that all you see is the edge of the paper. And these two bars are meant to be the edges of the parallel plates. Then I'm going to actually connect them. And I'll connect them with an EMF and a resistor, just because usually you don't have an EMF all by itself without some kind of resistance. So we have our EMF and a resistor. The resistor here doesn't actually do anything, but the EMF is going to remove electrons from the positive side and deposit them on the negative side, which sets this up as a capacitor, and then it actually sets up an electric field in between the two plates. So in this case, the right side will be missing electrons, and those electrons will be deposited on the left plate. This sets up an electric field in between these plates. And you might remember from Chapter 2 on electric fields that one way to set up a uniform electric field is to create charge distributions that have an area of positive charge parallel to an area of negative charge, exactly like this. So we have plate 1 on the left, plate 2 on the right, and we have a distance between them that I'll just call small d. So when the plate area is much, much bigger than the distance between the plates, we can treat the plates as infinite planes of charge. And therefore, the electric field between the plates is equal to the contribution from plate 1 and the contribution from plate 2, and that simplifies to sigma over epsilon naught. And I'm just working with the magnitudes here because the electric field from plate 1 would be to the left, because it's towards negative, and the electric field from plate 2 would also be towards the left because it's positive, so going away from positive. And so I'm just adding up the magnitudes. And you might remember from Chapter 4 that the potential difference for a path through a constant uniform electric field is equal to negative E dot delta S. And in this case, delta S is going to go from the negative plate, from plate 1, to the positive plate, which is plate 2. So then, since the electric field and delta S are opposite each other, I can just use the magnitude version of this. So I have E times delta S times cosine of the angle between E and delta S, and that works out to negative sigma over epsilon naught times d, because the distance is d, cosine of 180 degrees. Cosine of 180 degrees gives negative 1, so the negatives cancel out, and I get delta V from the negative plate to the positive plate is equal to sigma times d divided by epsilon naught. Then remember that sigma was the surface charge density, and that's just equal to the total charge on one plate divided by the area of the plate. So I can substitute that in, and then I'll actually have delta V in terms of the charge and the area on the plate. And delta V going along the path delta S is really just the potential difference across the capacitor. That's equal to Vc. But remember then the voltage across the capacitor is equal to Q divided by the capacitance. So I can substitute that in, and I have Q over C is equal to QD over epsilon naught A. Then the charge Q's cancel out, and I can invert both sides to find the capacitance is equal to epsilon naught times A divided by D. This is only true for a parallel plate capacitor when the area is much, much bigger than D. If the area wasn't much, much bigger than D, then we would not have been able to treat the plates as infinite sheets or infinite planes. And that would have complicated this quite a bit. Anyway, at this point, the value of this derivation is more in terms of tying a whole bunch of ideas together. And it's also helpful then to actually understand what these different terms mean. That A is the area of the plate, and that would be in square meters. D is the distance between the plates in meters. C is the capacitance in farads. and epsilon naught is the permittivity constant.